Okay, let's talk about oscillations. This is going to be oscillations. And what do we have here? Okay, oscillations and position. Oscillations and position. So we have our little oscillator here. We have our spring right here. And we have our little mass here, particle with a mass. And we're going to displace it. So it's going to go this way. This is going to be the floor right here. So you're going to give it a little displacement, and it's going to go all the way here. Okay, let's do this a little better. So it's going to be displaced all the way here to this point over here. And this is going to be your displacement right here, and this is going to be your amplitude. Okay, this is going to be the amplitude, and let's say that the amplitude is going to be equal to 0.5 meters. And remember that you have a force coming this way, which is the restoring force, and that force is going to be equal to minus kx, where k is going to be the spring constant. It's going to be 120 Newton over meter. And this particle has a mass, and the mass is going to be 2 kilograms. So the mass is 2 kilograms, the mass of your particle. And once you let it go, it's going to start to oscillate. It's going to go back and forth. And you can represent that with a function. So we're going to do a little function here, because it's going to go back and forth, back and forth. And it's going to go like this. So let's do the other axis over here. There we go. So that's going to be the axis. And this is going to look something like this. It's going to oscillate all the way here and then here, and so on, like that. And okay, let's give it a little more axis right here. There we go. So this is going to be your time, and this is going to be your position right here, and this is going to be your amplitude right here. So this is going to be over here. This is going to be your amplitude. Your amplitude is going to be 0.5. So this is going to be over here. It's going to be 0.5 meters. It's going to be meters. And this one is going to be minus 0.5 meters too. And that's going to be your amplitude right here. This is going to be amplitude and your minus amplitude. So it's going to start to oscillate over here at the top. This is where it starts oscillating. It's going to go back and forth, and it's going to go all the way over here. You can have one period. So that's going to be one period of the oscillation. All this distance here. This is going to be your period right there. It's going to be from here, for this point right here, to this one right here. Oops, there we go. Let's make it a little better here. Let's erase this. So this is going to be your period right here. Okay, let's make it kind of straight here. And okay, so this is going to be your period right here. And let's calculate the period. So how can we do that? Well, we have our formula that says that the period is going to be equal to 2 pi over the angular frequency. And we can calculate the angular frequency. The angular frequency is going to be the square root of k divided by m, where k is the spring constant divided by the mass. So your angular frequency is going to be 120 Newton over meter divided by 2 kilograms, and we got to get the square root of all that. And your angular frequency is going to be the square root of 60. And if you do all this conversion of the units, you're going to end up with 1 over second square right here. So this is going to come out as 7.75 seconds to the minus 1. And this is going to be your angular frequency. So this is going to be equal to 6.28 divided by 7.75 seconds to the minus 1. So your period is going to come to be 0.8 seconds. And there you go, you got your period right here. So that's going to be in your picture over here. It's going to be the period this time right here. It's going to be 0.8 seconds. And that's going to be your period. And you can say that this part here is going to be 0.2 seconds. And then you got this middle part right here. It's going to be another. So this is going to be 0.4 seconds because 0.2 plus 0.2. And then here it's going to be 0.6 seconds. And here is going to be the 0.8. So what's happening here? Well, you go from here to here and 0.2 seconds. And then you got this part over here. You go from here to here. And that's another 0.2 seconds, which makes 0.4. And then from here to here, and that's 0.6. So that's 0.2 plus 0.2 plus 0.2, that's 0.6. And then from here to here, and that would be another 0.2. So you got 0.8 seconds in total. And that's going to give you your period. And you can see it as like this if you have a whole turn right here. So this one here, this would be the first one. This one here would be number 1. This would be number 2, number 3, and number 4 area. So this would be number 1 right here. Number 1, and then this one would be number 2, number 3, and number 4. And you go all the way around, and you end up at the same spot over here at this point. And that's 1 period. So all the time it takes to go around and land at the same spot over here, that's the time it takes you to do all that, that's your period. Okay, so now let's calculate the position at a time. Let's put it over here. We want at a time of 0.5 seconds. We want to know where our particle is. Okay, so let's get our equation here. So our equation says that x is going to be equal to a cosine of omega t. And that's the equation that represents this function over here. X is equal to a cosine omega t, with omega is the angular frequency. And we're not going to talk about phase angles right now. We'll do that later. So now x is going to be equal to 0.5 cosine of, well, we got the angular frequency. The angular frequency is 7.75 right here. So it's going to be 7.75 seconds to the minus 1. And the time that we are interested in is 0.5 seconds. Okay, and seconds are going to cancel with seconds to the minus 1. So x is going to be equal to 0.5 cosine of 7.75 times 0.5 is going to give you 388 radians. because this is going to be in radians. And you have to convert the radians. Let's see. So you're going to multiply 1 radian. I'll do it over here. See, 1 radian is equal to 57.3 degrees. But we have, this is 3.88. We got 3.88 radians. And we want to know how many degrees are there. So X, we multiply 3.88 times 57.3. So we get 0.5. Cosine of 222.3 degrees. Now we got degrees. And X is going to be equal to 0.5 meters. This is meters right here, meters, times the cosine of that, of the cosine of 222.3, which is going to be minus 0.74. This is a 74. And X is going to be equal to minus 0.37 meters. So you got your position at a time of 0.5 seconds. So where's that going to be? Well, let's check it out. So it's going to be around here. This spot here, this point here is going to be minus 0.37 meters. And it's going to go all the way here with this one right here. And then you're going to go up here, right here. This is where they intersect. And that's going to be your time of 0.5 seconds. And as you can see, let me make this a little more straight here. At a time of 0.5 second, your particle is at the position of minus 0.37 meters. So that's going to be over here, someplace around over here. On this side, on the negative side here of the displacement. And there you go. So you have your position at any time. And you have another problem here.